transforming exponential equations. So this is like our parent function. This is our exponential equation. And technically an exponential equation, the base can be any number. So I could use a variable to represent it, but then it becomes an equation of just variables. So we're going to choose the base of 3. These rules apply if it's 2, 4, any other value. And they all apply, okay? So we've used base 3, and then we have the values of a, k, d, and c. And these are values you guys have used before in transformation. So I'm going to use, do you guys remember this function here, the root function? Did you ever remember using a, k, I should highlight them here. Your a would normally be here, there'd be a k in front, minus d, and then a plus c at the end?
Yeah.
Yeah. So what that is these follow the exact same pattern for every single transformation you ever make, okay? So your a function here is going to be vertical stretches and compressions, okay? So we're going to say a is vertical, stretches, compressions, and flips actually too. If it's a negative value, it's going to flip it on the x-axis. And our c value is going to be vertical translations. So plus goes up and negative goes down, okay? Our k value is going to be horizontal stretches, compressions, and flips again, but they're a little of the opposite. And d is going to be horizontal translations left and right. The only difference here is usually positive is to the left and negative is to the right.
Yeah, because the
negative
because the equation is like mainly negative.
The operation is a negative inside. So as long as you can remember those rules, the only thing you really need to know is a couple points along the original function. So there's like a mapping notation you could always use to solve something like this. So what I'm going to do is do some really basic ones to start. So let's say our f at x, well, technically it's a whole new function. I shouldn't call it f at x, but we'll call it g at x so that we are using the right function notation here. G at x is equal to 3x plus 2. What does the 2, thank you, what does the 2 represent? Which of these variables is 2 represented? Is it the a, k, d, or the c? It would be, which one? It's the c. Okay? So what this means is this is positive 2. The original 3x, or x to the power, 3 to the power of x would go up 2 units. Yes, I know you've discovered something. Daddy's gonna. Let's see what that would look like. We go over to decimals here. We have 3 to the power, oh, I don't want it of 2. I want 3 to the power of x. So here's our function. We can kind of zoom out a little, right? The second one we talked about is the exact same stuff above. Let's just paste it down here. But we're going to actually add the value of 2. And if you notice, this function here was crossing the y-axis. We'll zoom in a little. Was crossing the y-axis at 0, 1. It's now crossing it at 0, 3. So in other words, it's shifted up 2 units. Okay, so that's our vertical transformations. Let's go back. If we give you another function, h at x, and we say it's 3x plus 3 up here. Well, the 3 in this case is going to be dealing with d. And because it's positive, it's actually going to move that function to the left 3 units. So let's take a look what that would look like. We have 3 to the power of x, and I said plus 3, I think?
Yeah. No,
yeah, I think I got it.
Yeah, I think it was plus 3.
Plus 3. There we go. And you'll see that this point right here, can I get on it? There you go. Is 3 units to the left of our original 0 and 1. So you can see the coordinates kind of really show you the translations easiest, right? Now, the next thing we're going to work with are stretches and compressions, which are a little more complex. We have GH, say I at x. If we say the a value here, I'm just going to write them in since we kind of can deduce what they are from here. It's going to be 2 times 3x. Okay. What this means is this is going to be stretched vertically by a factor of 2. So think of it like you've taken an elastic band and pulled it upwards. So it's going to get thinner and thinner. So when I go to the other equation over here, we take 2. There we go. And you'll see the purple one in reference to the red one. You'll see that it takes off much, much quicker. Okay, it's been stretched vertically, but that coordinate's still the same. Okay, that's a major coordinate with our exponential function. 0, 1 is going to be the same one for all of them because anything to the power of 0 is actually equal to the number 1.
Yeah.
Okay. And then finally, the last one we're going to talk about is Gij, j at x. Say 3, and we'll use the number 4x here. 1 sec. Okay, so 3 to the power of 4x, there we go, is going to be pretty different looking too. And what's actually happening is this is being horizontally, thank you, it's being horizontally compressed by a factor of 4. So think of it like we've taken kind of like compression from both sides, kind of like a composter or a garbage compressor, and it's pushed everything inward. So it actually ends up looking like it's vertically stretched.
Yeah.
Okay, which are the exact same rules of all the other one. The toughest part is